Hello, my name is Lily Alterman, and today I'll be presenting to you Lab 4 Oscillations. Now, the purpose of this lab is to examine the motion of a spring mass system. This spring mass system will have the mass swinging in an arc while oscillating on a spring. And from this, we're going to determine whether this model follows the energy principle. Now, Newton's second law is also known as the momentum principle, and this relates the total interactions to the changes of motion in the system and can be seen by the following formula. Next, we have the law of conservation of energy, which then relates the change in the total energies of the system, which can be seen by the formula right below there. And we also have Newton's second law, which gives us the velocity and position update formula, which will be very useful in our coding and modeling later in this lab. And then work is also viewed as the dot product of force and displacement. If it is a constant force and constant displacement, it will just be the dot product of the vectors, but it will be the integral of the dot product if this is a non-constant force. Next, spring potential energy exists due to the stretch or compress of the spring and can be represented by the following formula right here. And then the gravitational potential energy is the potential energy associated with the gravitational interactions, or basically the force of gravity, and can be seen by the following formula. And then finally, kinetic energy is the energy associated with motion. Anything that's moving has kinetic energy, and that is represented by this formula right here. Now, in this lab today, we will be using the modeling programs WebPython and Tracker, and as a little note, all the initial values for the calibration length, time between the video frames, and some of the physical characteristics of the systems, like the mass or like the string stiffness, are all given from the 52 pre-lecture video. And if you're interested, you can go check that out. And to the right here, this is just a snapshot and a little sneak peek of the spring mass system we will be looking at today. Now, the initial conditions. We can assume that there's no work from the surroundings on the system, and there is also no Q in our energy formula. So the change in energy is just going to be the work in this case. And we can also assume the change in energy is 0. Now, the system itself is the spring, the mass blocks, all fixed to a point, and technically there is a hand to start the oscillations, but since we are having that as our starting point, we are still saying there's no work from the surroundings on the system. And if you look to the right over here, we have our free body diagram, and our two forces are the force of the spring and the force of gravity. And since those are in directly opposite directions, we can say that we can't set those two equal to each other, which will be very useful for some calculations later. Now, this is our tracker simulation. Right here, we have our video of the simulation, and as you can see, our spring is oscillating in the system, and we are getting a whole bunch of data points we will analyze. The most important thing to note is that we did have our given mass as 0.402 kilograms, and we did have our given L vector to be 0.7 meters. Our initial velocity is 0, and our initial position, which was taken from the tracker simulation, ended up being negative 0.139, negative 0.6730 meters. Now solving for unknown conditions. So between the top of our little graph right here, for example, this is the mass A, and then this is Y. So we're looking at Y on our Y-axis, and then we're looking at time on our X-axis right here. And basically at the top of these peaks, we're saying that is our T, or aka our oscillation period, which can be found by the following formula. We then use that to calculate that K should be 9.234 Newton meters. And then by setting the force of gravity and force of spring equal to each other, in solving, we are able to get the L naught length to be 0.123 meters. The following is the WebPython simulation. The initial conditions were defined as found in the tracker in the previous slide, and they were just put right here in the code. So we then used the WebPython to calculate the energy of the system and the spring length with the following formulas related to each section of code. So the top little subsection of code was all relating to spring length, and the bottom was all related to the energy of the system. The following is now our motion prediction / the simulation loop. We basically changed T up here to fit the time of my video, and by applying the formulas like the position and velocity update formulas and all of our energy formulas and constants we described above, we are then able to simulate this experiment. Now this is the WebPython simulation. As you can see, my function runs, and we're getting data points actively and correctly modeling the motion of our system. Then our results, some possible errors could be that the system is not really having zero outside work done to it. Sadly, in real life, we don't just get to negate the outside work, and it's very clear that something else could have been causing the motion to be like this, considering the difference in my graphs, according to the model and experiment for the Y position. And also, most likely, the most prevalent error was the inaccurate and not precise placement of the center of mass for the tracker simulation. While I tried my best, obviously by these graphs, you can see that my eyeballing and my lining up was not as good as the simulation and did not account for the perfectness that the simulation did account for. Now, the what if and what those questions, what does it mean? So basically, is the energy principle satisfied? Yes, it is. There is no external forces acting on the isolated system in our examples, and the energy must be 0, so the total change in energy on the graph is also 0. And you can see that through the basically positive and negative almost basically canceling each other out and getting us our little orange line here. And then basically I used my data from Tracker to estimate that the X time period is approximately 1.6 seconds, while the y estimates to be 1.5 seconds, and the fact that these are different proves why it's best to calculate the spring constant using oscillation periods on more than one axis, because these axes have different values. Thank you so much for listening, and I hope you have a lovely day.